Welcome back to another video, everyone. I hope you're doing all right. And in this one, we're going to be taking a look at some problems that are going to be involving three-dimensional geometry. So if that's been the source of trouble or pain or perhaps even anxiety for you, you've come to the right place. So let's go ahead and dive into some problems. So here we're given a cuboid with a pretty lengthy name, A, B, C, D, E, F, G, H. And that's about it. So again, that's just in reference to A, B, C, D, and E, F, G, H right here. It's just giving you kind of what the name of the vertices are. Remember that the vertices are basically the corners of a cuboid. And a cuboid's kind of like a cube, except it's just not, well, a cube. It doesn't have equal lengths for its length, width, and height. It's a little bit different. So in this case, we have dimensions of 4, 5, and 6. All right, so we have a 4 by a 5 by a 6. And what we want to find is the length of diagonal from D all the way to F. So it's kind of that front left corner going to that back right corner. So it's going across. And we want to figure out what the length of this DF length is. And we want to figure out what the size of BDF is, this angle kind of situated right here. So if we want to find the length of diagonal DF, let's think about this. We want this diagonal right here. And I know that right here is going to be 6 centimeters because that's the height. And so now I kind of have this triangle right here that I'm working with, and I'm going to have a right angle. So if I actually kind of draw this out, I would have a triangle that looks a little bit something like this. I would have a 90-degree angle. Forgive me that it's not perfectly to scale. And so I don't know what D to F is, okay? And then here would be B. So you might be looking at this and thinking, well, I don't know what the other two lengths are, so there's not really a whole lot I can do. However, there's also this triangle down here. So if I actually drew this, like so, another right triangle. So when I extract that triangle out, I'll have D, and then B, and then over here I'll have C. So I know that DC is going to be a 5 centimeter triangle, 5 centimeter length, and then BC would be 4. And I know that this is a 90-degree angle because, well, that's just going to be kind of the nature of what I'm pulling out. Because remember, this is going to be essentially a rectangle, which means that all of these right here are going to be 90 degrees. So if I have a 90-degree angle here, I have 5 and 4 here. I can go ahead and use the Pythagorean theorem to figure out what my missing length is. So I know that dB squared is going to be equal to 5 squared plus 4 squared. And if you put that into your calculator correctly, you'll find that the length for dB is going to be equal to root of 41. And I'm going to keep it as the root of 41 instead of a decimal because, again, what we touched on in our last videos is that in the calculation part, you want this to be as accurate as possible. And since the root of 41 is going to give you an irrational number, meaning it is a decimal that goes on forever without repeating or finishing, the radical expression is going to be the easiest to work with for your calculator. So if I know that dB is the root of 41, I can go ahead and put that here. I can also label my diagram here. So the root of 41 is right here. So now I know two sides here. I know 6 and the root of 41, so I can go ahead and solve for df by, again, using the Pythagorean theorem. So my value of df squared is going to be equal to the root of 41 squared plus 6 squared. So the df is going to be equal to the root of 41 plus 36. And if you put that all into your calculator correctly, it should spit out a value of around 8.77. Around 8.77. Now you might be wondering, why am I not leaving it in radical form? And that is an acceptable answer. But in our context, especially in the IB program, we really want to focus on 3 significant figures. And since we are asked for an answer, we're going to go ahead and put it into 3 significant figures. However, leaving it as a radical is also correct with your calculations. All right, so there again, I went ahead and did A. So now I want to find the size of that angle D of BDF. So I really want to find out what this angle is right here. And that actually isn't too bad because if I think about this, well, look at my angle and look at the size I'm given. I have opposite and I have adjacent. So what trigonometric ratio uses opposite and adjacent? That's going to be tangent, the TOA. So the tangent of my angle is going to be equal to opposite over adjacent, which means that theta is going to be equal to the inverse tangent of 6 all over the root of 41. Now, if you go ahead and put that into your calculator and do it to 3 significant figures, you'll get an answer of 43.1 degrees, and there we have it. Okay, so just like that, I use some basic properties, in this case the Pythagorean theorem, twice in order to figure out what my missing length was. And then I'm also using those lengths within a trigonometric ratio, in this case the tangent, to figure out what my angle is. Let's take a look at another problem. So again, I'm giving another cuboid with a pretty intimidating name, A, B, C, D, E, F, G, H. Again, it's just naming the vertices, it's just talking about this cube. And it's going to have dimensions of 4, 5, and 6 centimeters, as is already shown. Okay, I have 4, 5, and 6, so that checks out. M and N are the midpoints of DH and BF respectively. So what that means is that this is equal to this, and this is equal to that. Okay, so let's go ahead and find out what the angle of NEM is. So what we're thinking about is this angle right here. All right, kind of a hard thing to maybe visualize, but if you extract out the information that we need into a different diagram, it might help you out a little bit. So this is the triangle I'm focused on, MEN, and I want to know what this angle theta is here. The problem is I don't actually know what any of my lengths are, and that could obviously prove to be problematic. However, if we break this down a little bit by looking at our diagram over here, I know that I have MN as kind of cutting off HD and FB into 2 equal parts. So if the entire height is 6 centimeters, well then this right here must be 3, this here must be 3, this is 3, and this is 3. Now, again, pulling out the triangle that I kind of need to take into consideration, if we think about this kind of going from M to E, well, I know what this is, and I also know what this is, because if this has a length of 4 here, well then this is going to have a length of 4 up here. Which means that if I know that this is a 90-degree angle, I can figure out what ME is by, again, using the Pythagorean theorem. So if I actually drew that out a little bit to kind of help. So now I'm kind of looking at it face forward. So I would have M, I would have E, and I would have H. 90-degree angle, I have 3, I have 4. I need to know what ME is going to be, so that way I can put this value in over here. So again, ME is going to be equal to the root of 4 squared plus 3 squared, just by using the Pythagorean theorem. So ME is going to be equal to 5. So ME is going to be equal to 5. ME is going to be equal to 5. Now, so what I'm going to do now is I'm going to go ahead and clean up this diagram just a little bit so it's still easy to work with. So I now know that ME is going to be equal to 3. So I don't know what MN is, and I also don't know what EN is. And that might be pretty useful to solve this problem. So E to N is actually a pretty easy one to figure out, because just like what we did with MHE triangle, we can pull out this triangle right here and solve for that, because I know that up here is going to be 5, and I know that this is going to be 3 right here. So what would my hypotenuse be? Well, I know that EN would be equal to the root of 5 squared plus 3 squared, giving me an answer of EN as equal to root of 34. Okay, 25 plus 9, 34. And let's go ahead and leave it like that. So the root of 34, just like that. So now I can't say that this is a 90-degree angle because there's nothing indicating that. And based off my other and based off the way that I approached the other triangles, I was able to figure out that this is 3. And if I clean up just a little bit more, this right here would be the root of 34 going down like that. I know that EN is going to be going down just like that. So now, what is MN? Now this is where it might look a little tricky, but if you think about this length from end to end, it's going perfectly across, right? Which means that this down here is also going to be the same length, because it's just going from one corner to the other corner, the same way that this is going. And since I know that this is 5 and 4, and this is a 90-degree angle, I can use the Pythagorean theorem again to figure out what dB is. I'll go ahead and put that in a different color. So I know that my dB is going to be the root of 5 squared plus 4 squared, which means that dB is going to give me a length of root of 41. Looking at my calculations. Okay, so now I have dB is the root of 41, and dB and mn are equal. So dB and mn are both the root of 41. So here I have the root of 41 like that. which means I have the root of 41 here. Okay, now what I'm going to do is look at this and I say, hey, I want to know the angle and I know 3 sides. Is there a property or a rule that we've gone over previously where we can figure out what the angle is given the 3 sides of a triangle? And the answer is yes, it is the cosine rule. So again, look in your formula packets, whatever it is that you have, and if you remember that the cosine of the angle is going to be equal to, at least in this case, it's going to be 5 squared plus the root of 34 squared minus the root of 41 squared all over 2 times, in fact, let me get rid of the x's, 2 times 5 times the root of 34. Now again, it can be a little bit complicated when you're not looking directly at the formula, but just remember that it is the 2 angles right here, when you square them and add them together, that are sandwiching the angle, subtracted from the one that is opposite of the angle. And then down here, we use the same 2 numbers over here that kind of sandwich that angle or create that angle, 5 and root 34. So if you put that into your calculator, remember, we're going to be looking for the inverse cosine of this. Okay, so that's what you should be putting in your calculator, the inverse cosine of this. And what you'll find is that the theta that we've been looking for throughout this entire problem is going to be 72.0 degrees to 3 significant figures. So again, that problem is a little in depth. You have to recognize a lot of, hey, what sides do I know, and how can I use that to formulate a multi-step approach to figure out what my area is? Because it's not exactly very straightforward. But again, if you just use the clues that were given and use the Pythagorean theorem, you can get all 3 sides of the triangle and know that the cosine rule gives us the angle when we have the 3 sides. So I hope that helped shed a little bit of light into how some of these trickier problems can be approached. And the next one, we'll also take a look at a tricky problem. But as long as we follow these steps, we'll get it right every single time. See you in the next one.